Okay, welcome back to my channel, everyone. My name is Ansar, your helping hand, and in today's video we're going to be doing another walkthrough of an IFoA question. Specifically, this question has to do with the central limit theorem as well as the exponential distribution. And yeah, it's going to be exactly the same as all my other exam question videos. I'll read out the question, give you some time to pause the video and attempt the question yourself, and then come back for the answers. So yeah, let's get going. Just a quick info recap. This question is from the 2017 paper in April, and it's question 5. Okay, so the question reads as follows. Consider 10 independent random variables x1 through to x10, which are identically distributed with an exponential distribution with expectation equals to 4. And then the questions are, the first one is specify the approximate distribution of x, where x is equal to the sum, including all parameters using the central limit theorem. Question 2 is calculate the approximate value of the probability that x is less than 40 using the result in part 1. And then part 3 is calculate the exact probability that x is less than 40. And then the last question is comment on the answers in part 2 and 3. Okay, so hopefully you're going to pause the video at this point and attempt it on your own, and then come back when you're ready to get the answers. Okay, I'm assuming you have attempted the question. Now, as always, it's kind of good to, before you start answering the questions, just to define some notation or just to put down the information that you know about the question. So we know that our xi's, right, xi or x1 through to x2 ... all the way through to x10 actually. These are all independent and identically distributed because they say independent and identically distributed with an exponential distribution where they say our expectation is 4, and the reason they say our expectation is 4 rather than giving you a parameter value is because there's two versions of the exponential distribution depending on what parameter value you use, but we use the beta value, and beta is always just equal to your expectation. So these independent and identically distributed random variables have an exponential distribution where beta is equal to 4. Okay, so the first question, and therefore we know that the expectation of any one of our xi's is equal to 4, and the variance of any one of our xi's is equal to 16. That's just important for the next part. But the first question says, specify the approximate distribution of the sum, including all parameters using the central limit theorem. So this question kind of tells you exactly what to do. And I have multiple other videos where I go over the central limit theorem. And basically, what the central limit theorem says is that the limit, so there's two forms of the central limit theorem. You can do it in terms of the sample average, which says that as n goes to infinity, the square root of n x bar minus mu over sigma is standard normal. So that's the pure form of the central limit theorem, but obviously we can't really work with infinities, so that should look like that. So instead, right, if you rearrange this in a particular way and you don't really want to work with your sample average, you can work with the sum instead, where if you're going from 1 to n, that this is going to be approximately, and it's going to be better approximated as n gets larger and larger and larger, where this is also going to be a normal distribution where our mean is going to be n times the mean of any one of our xi's, and the variance is going to be n times the variance of any one of our xi's. So using this is what the central limit theorem kind of says, either this or that, whichever one is more important to you. Obviously this one is more important to us because they say we need to use the sum. So therefore we can say that x, which is equal to the sum from I is equal to 1 to 10 of our xi's, is approximately a normal distribution where we've got 10 times our expectation, which is going to be 4, right? Because the expectation of any one of our individual random variables is 4, given what we have in the information in the question. And the variance is going to be 10 times the 10 times the variance of our individual exponentials, which is going to be 10 times 16. So therefore, we have that x, which is the sum, is normal with mean 40 and variance 160. Okay, so that's the first question, just specifying the distribution, including all parameters. Question 2 says calculate the approximate value of the probability. So the approximate value of the probability is, because we're using the approximation, is going to be equal to the probability that x is less than 40. Now, because we have this approximation that x is a normal distribution, we can calculate this probability very easy if we standardize things. So we're going to take x, subtract our mean, divide by our standard deviation, which is the variance square rooted, is less than 40 minus 40 over the square root of 160. So this over here is a z value, right? A z random variable, where z is a standard normal, and this value over here is just going to be 0, because 40 minus 40 is 0. So this is the probability that z is less than 0, which, if you know anything about your normal distribution, you know it's just going to be 0.5. Okay, so that's the second question. The third question is calculate the exact probability that x is less than 40. Now, the exact probability that x is less than 40, we need to know what the exact distribution of our x value is. Sorry. And we could kind of work it out, but I have a separate video that specifically deals with working out what the sum of exponential random variables is. So I'm just going to kind of tell you the result, which is basically whenever you have the sum of from 1 to n of, I'm going to call these yi's, where yi's are exponentials with beta, right? Anytime you have the sum of exponentials from 1 to n and they're independent and they're identically distributed, so they have the same beta and they're all independent, that this sum s is a gamma distribution and not an approximate gamma distribution. It is a gamma distribution exactly, where your alpha value is the number of exponentials you took and the beta value has the same beta as your original exponentials. So that's just a kind of result that I have proven in a different video where they ask us to prove it. But this, because we know that the s, our s, which is our sum, has this distribution exactly, we can figure out where, this is I, we can figure out the probability that s, where, actually I'm just going to write, instead of writing s, I'll write our actual value where we have x, that x is less than 40, is equal to the probability that x is less than 40, where x is some gamma, where x is gamma, and we took 10 exponentials, and our exponential had a beta of 4. So you could go and do this probability exactly, right, of that x is less than 40. And if you did do that, right, I'm just going to quickly get up our studio to get this probability because I don't have a table with me at the moment. Q is equal to 40, shape is that is 10, and scale is 4, and look tail is true. Sorry, I'm just getting the probability. So this particular question, the actual probability requires that you have a table with gamma distributions. Alternatively, you can standardize your gamma distribution to make it a chi-squared, where you take 2 beta x, and that will be a chi-squared with 20 degrees of freedom, if I'm not mistaken. So you could do that as well and try and find the probability that 2bx is less than 2b times 40, and that you could possibly do in your chi-squared tables. But actually, if you try and work that out, it also really won't work because our tables don't have values for your chi-squared in that range. So essentially, you do need statistical software to calculate this, or tables that have these distributions in them. But that's kind of not really the point of the question. It's just calculate the probability that this is less than 40, and however you calculate that, you're going to get this being equal to 0.542. And obviously, we wouldn't be able to calculate this in an exam, but they also wouldn't give this question to us in the exam if you're not actually able to calculate it. Obviously, if you've got a computer, if you've got Excel, if you've got R, if you've got a table that has these values, then you can do it. So yeah, that's question 3. And then question 4 is comment on the answers in part 2 and 3. So here we can see that in our normal approximation, right, we've got 0.5, and in our exact probability, we've got 0.542. So our n value is not very large. It's small, right? It's 10. It's only 10. Most of the time when we use the central limit theorem, your n is going to be much larger than that, 30, 40, 50, 100, more than that, right? So our n is quite small, but our probabilities, right, the probability that we calculated, right, was accurate, or our approximate probability, right, that was accurate to one significant digit, So if you need one significant digit, then, I mean, this is a great approximation. If you need more than that, if you need more accuracy, obviously you just need to take more samples. Okay, so that's question 4. Okay, so that's the end of this video and the end of the question. Please don't forget to like and subscribe, comment if you have any questions or requests. And yeah, I'll see you in the next video. Okay, bye.